Okay, so everybody's gotten the cursing of me out of their system because you didn't know what you're doing. You're just running the stuff. What's really good is I know that every one of you presumably now have run that initial Python notebook, which means you should have the technology set up and not run into technical issues over the next few days. So let's actually start diving in. What did we do yesterday? So what I kind of tried to outline is, at this point, you should know the basic components necessary to produce an ML model. In other words, remember that triangle going to a black box? There's something called backpropagation. I heard this word epoch. You have an example of model equals and then a bunch of layers. And that should give you an example of how I can actually construct the topology of what's in that black box. You saw that line, model.compile. So you now actually, believe it or not, know how to compile a model. And you know how to train your model. You call it fit, which is good. So then one common question that gets asked every AI tutorial I was at, there'd be at least one physicist who would ask the data scientist the following question: how do I know which technique to use for my problem? And always the data science person would give the most kind of wishy-washy answer. It depends. You don't really know. There's not an algorithmic formula. Like you don't, you're sitting in a first year of physics class mechanics, and Bob throws a ball and you immediately go, kinematic, equations. I know F equals ma. It doesn't work like that for this exactly. So there isn't really an analytic solution. I can't give you an algorithm that says, if this, then use convolution. If that, then use this other thing. But you need to have an understanding of what your objectives are and what your data is. And so, for example, a common one is I'm using images or things that I can shoehorn into looking like images. That might mean that I should be using convolutional neural nets or convolutional layers. Why? Because people have had success with it. Other problems. Do I have to? No. Is it always better? Not necessarily. So it's more of you get your feet wet, you start playing around with it, you see what works, you see what doesn't work, and you come up with a little cookbook. One of the things that I had in there yesterday was this activation function, which I was in the code, and I didn't mention it all. I kind of did that on purpose because when you start looking at an individual neuron in a dense layer, say, it's actually got several components. And the activation function, if you'll recall, is like the last thing that the neuron does before it passes its answer downstream to the next layer, or the neurons in the next layer. And there are a bunch of them. Sigmoid, ReLU. ReLU is very common. Linear is not listed here, but it can be used, is used sometimes. TANH, sigmoid, max out. These are not an exhaustive list. Hey, can I write my own? Sure, if you want. We're not going to be doing that though, because again, shallow end of the pool. And then for those that really wanted to know the math, I'm trying to stay away from it, but I put two links. I really, toward data science, I cannot recommend them enough. They have really good articles that step through the math and how you arrive at backpropagation mathematically. In this case, I stole this from toward data science. And the one thing I will say is, when I say loss function, other people might say cost function. So these C's are really the loss. It's just a nomenclature thing that's changed over the last couple of years. People have started saying loss, and cost is more referring to like reinforcement learning stuff, but it can be used interchangeably. So I put these here for those that are interested. And now I want to spend a little bit of time talking about the data. So if you recall from yesterday, there was val_loss. And I got many people asking me, what is val loss? But how does it differ from loss? Great question. I'm glad you're here today. So we have some block of data, And there are three main buckets that this data will end up in. The train set or the training set, the validation set, or the val set, and then the test set. Depending on who you're reading, who you're talking to, these will often be interchanged, and I'll describe why in just a moment. So I sit down, I have this block of data, and I need to have some part of it in training and some part of it in validation. Generally, a lot of examples you see use an 80-20 split, 80% in training, 20% in validation. The thing that makes train and validation the same is both of them have labels, target values. So when I'm teaching my son, I tell him, you know, yeah, this is a dog, this is a cat. Whereas the test set, I don't tell him. You need to have the answer so you can compute the loss so you can do the back propagation. Passing back out the flash drives, you can also download it from JLab's user web from the Indico link. I modified the slides. So just to make sure everybody has the most up-to-date slides, trying to respond to people's needs. The other critical thing is the validation set is never used in training. And by that, I don't mean the training process, because clearly it comes in. I mean, it's never used to modify the weights. It's not involved with the back propagation. And this is because I don't want my son to tell me, read the same book a million times and memorize, say, the order of the book. And I need him to see novel images, ones that haven't possibly been baked into his neural net as a memory. I want him to abstract those concepts to take a novel image and tell me if it's a cat or dog. There is an assumption baked in here. It often goes unsaid. The validation data comes from the same distribution. And what I mean by that is if I have a training set that's full of cats and dogs and my validation set is full of lizards, things won't go well because the model is not, lizards aren't from the same distribution. It's nothing like the images that he sees. And he only knows how it's cat or dog. That's a really weird cat or dog. So oftentimes if you get a decreasing train, but the validation is always bad, it could be an indication that your validation set, for whatever reason, it does not come from the same distribution. Maybe you got unlucky, it's a small data set, and you have a couple of outliers, and all your outliers end up there. Your model may have a problem. Yep.
Do you shuffle to get rid of that or no?
So great question. So the question is, do you shuffle to get rid of it? You do shuffling to get rid of overfitting, which we'll talk about in a bit to prevent the memory as much. There's something called cross-validation, which is beyond the scope, but I'll describe it briefly. Cross-validation is a way to say, how sensitive is my model to my selection of the training and validation? We won't be doing it now. Again, it's a little deeper in, not deep in, but medium up to your neck kind of a thing. So if you go Google, machine learning cross-validation or K-fold cross-validation, you'll see there are tests you can do to say, is my model really sensitive to what I put in my validation? That could be a problem. Often small sample size is the driver. And then we have this test set. And it has no labels or target values. And I put no in quotation marks because you might have data in which you have the labels, but you don't show the model. You don't let the model know, or the training algorithms. These would be new images, as if you're doing a self-driving car and you take a new right turn down a new road. This would be your test set. You don't know what that road holds. And generally, there is another function which actually I'm mentioning here, and then we will just probably not mention again. We did model.fit. You can call model.predict. And predict says, take in this data, give me your output, your answer. It's called running inference, is another term for it. And I believe PyTorch, TensorFlow, and most call it predict. So you could take novel images, feed them into model predict, it consumes it, and then it says cat, dog, or lizard if I have 3 categories, because it can be more than binary. So if I look at one of the train or validation sets, a piece of datum, one single entry, what I will see is that my set is comprised of X's and Y's. And this could be a variety of images and labels. This could be a bunch of a vector of numbers and a single number out. It is your input data and your target value, your label, what you want to compute the loss based on. All right, and you've got to keep them stitched together. Because if I take that fit call from yesterday and I post it up here, it's not exactly the same. I took it from tomorrow's fit call. You can see the parts actually sitting here. The fit takes in an X and a Y and validation data, which is comprised of the set of X's and Y's. So if I go back, this would be this vector here, this list would be my X's. This list would be my Y's. And then I'd go to the validation set and I would say, I have a different set of X's and Y's. You cannot mix the X's without mixing the Y's in exactly the same way. They're inextricably linked. And I hope that makes some sense, right? If I say I have cats and dogs, here are the images, son, and now I'm just going to randomize the labels. Good luck. That would make me a bad parent. Okay, so you also, most of you I saw plotted the loss and did a bad job of labeling all the axes. All of these have a loss on the Y and epochs or iterations on the X. And one common question is, how do I know it's learning? That's a great question. When the loss decreases, that's only a partial answer, because I could decrease the loss, but have a validation loss that increases. And at least one person had come to me and went, I trained for a long time. Why is my validation loss going up? And we're going to talk about it right now. So this is the textbook curve. And if you take yesterday's tutorial and you set it for 50 to 100 epochs, you say go, you get very close to this textbook curve. And what this shows is it takes the training set, which remember is what it's actually using to modify the weights. So it's doing the back propagation with this data, it's modifying the weights, and it's minimizing it. And it's able to arbitrarily get it as small as possible. But the validation data doesn't get a chance to modify the weights. So this would be the equivalent of overfitting out here. It only ends up learning that this collection of things are ones and this collection of things are twos. I've no longer abstracted out what it means to be a 1 versus a 2 in yesterday's example. Instead, what I've done is said, I remember exactly what the ones look like. Because that's another way to minimize loss, right? I don't have to get all possible things that represent ones. I just have to get my training sets. So we need to combat this. You do not want to have a model that does not generalize well to new novel data. So what you want to do is you want to make this, ideally, you would want to make these curves, plot these curves every time you train. Not sometimes, every time. And you want to look for this inflection point. And then it would have been great if we, reverse time, and our model we come out with is all the weights such that the training is minimum and we aren't increasing our validation. Not in the deep end, but again, the medium up to your neck, and we won't do it this time. There are callback functions inside TensorFlow, PyTorch, and the like. For TensorFlow, it's called early stopping. And this is such a common procedure where you train for a bunch, you look for this inflection point, and then you do one train that just ends there. And then you walk away and you go, don't train more. It's not actually better. And early stopping basically watches these curves, and you can parameterize how much, how sensitive it is to this inflection. And when it notices its inflection, it stops the training, it reverts the weights to what it was at the optimum when it detected the inflection. So it helps prevent this idea of overfitting. There are other shuffling your inputs to prevent memorization is another way to help combat this overfitting concept. And that's where I will drop it because we only have a few hours. So this is an actual training a colleague did for a project. And as you can see, the train and validation, they both go down, they do diverge. But this is a healthy train. So we probably pick a model that's somewhere around the 100 epochs. I don't remember what we exactly settled on, but doesn't really matter. So this is healthy. This does not indicate a problem. This is not healthy. So you'll notice that our training goes down, our validation goes up. Why might this be? We may probably, in this case, we have a small data set and the validation is not like the training set. They're not from the same distribution. So the model's learning how to abstract these things, but it never notices these things. All right. It's really important, that willingness to be wrong, because failures actually provide you data in ways that perhaps other analyses, you fail to fit, doesn't help you as much. It's not a good fit, it's not a good model. I have an anecdote, which I think illustrates this well. I was doing some work on a high voltage control module. Can we predict potentially when the capacitance of these three capacitors decreases enough that you can cause core saturation and the module explodes? Can we prevent that? Can we predict it early? And we were doing simulated data, and I got the simulated data, and the circuit had a symmetry in it. And my model exploited that symmetry by also having a symmetry in it. Yeah?
Symmetry.
So it had three main branches, and if you cut each branch and overlaid them, they looked the same. It's exactly the same branch on three different paths. So my model followed a similar thing. It had three branches that were identical. If it finds a correlation to one, it should find a correlation in all of them. And I could never get one of the capacitors to be predicted well at all. And I spent 3 months thinking I was doing something wrong and getting all this evidence. And I have a 100-page slide deck of all the little tests I did that failed and how they failed. And the only way this made any sense is if the data was wrong or the labels were wrong. And I said, the person who was running the simulation, I said, can you check for me that you didn't run ABC, instead you ran ABA or ABB? You changed the label, you said it's ABC, but the data you ran was ABB. 5 minutes later, he goes, oh yeah, that's what I did. It's like 2 months. And but I didn't have a success. I didn't have access to the code. But each failure and knowing the data, knowing those symmetries, allowed me to diagnose and debug code I didn't have access to. So your failures actually provide very valuable data. So this is supposed to be nuclear physics, particle physics. And so I've been, I guess, waxing poetic about the underlying neural nets. Let's actually try to do a toy problem. I highly recommend you go back to your institutions, you have the code, the Python notebooks, and you're going to try your own project. Start with one you don't need machine learning for, because then you know probably how it's doing it. So that's what we're going to do. I stole this from the hackathon, and so we're not going to be doing 5 problems unless you're really ambitious. Feel free, all the data's there. But we have a calorimeter. This is the BlueX forward calorimeter in construction. And it's a calorimeter. Each little kind of pixel or little block is like glass block. I think calorimetry has been mentioned. Don't need to know much about the calorimeter except for particles within cause shower, we detect energy, and so we would like to know where and how much energy was deposited in our calorimeter. We're gonna make this really easy. We're not gonna do all, is it like, now there's thousands of blocks. We're just gonna do a little square of it. No beam hole, just a little square, completely solid, and it's 100% efficient absorbers. And we're also going to say that all the particles are just like streaming down 90 degrees. We don't have to worry about angles, smearing, and overlapping. Could I do this without machine learning? Yes, I could do this problem without machine learning. That's not the point. The point is, can we do it with machine learning? So we have a 30 by 30 pixel detector, 30 blocks, 30 blocks. You can compute the size of each block. It's a square. Don't really need to know too much. This is our detector. And the data that's going to be given to you looks like this. Each one is 30 by 30 pixels. I just head off a question. Do I have to use the images? No, you could use a linear string, or you could use the images. I don't care, it's your data, you do what you want. So the 30 by 30 has individual clusters. These are nice, beautiful, round Gaussian clusters. Can I do it without machine learning? Yes. Am I going to? No. And each one of them contains 3 values of interest: the center of the cluster and the energy deposited. I think in this case, it's energy deposited in arbitrary units, doesn't matter, and the centroid of the cluster. All right. Later problems, this is problem 3, which we're not going to do, but I want you guys thinking kind of, how would I scale up this problem? What if you had multiple hits? Could you give me all the centroids and all of the energy deposited in each cluster? Then we did it with noise, and there was somebody who I don't think could make it, who was actually in this hackathon, and apparently our 5th problem nobody got, which is supposed to be a challenging problem, and I threatened to make you guys do that problem. I'm not going to do that. The CSV files will contain 900 columns per row, which represent the 30 by 30 block responses, and an additional set of target values. So the last 3 are your target values. So 903 columns, where if we're thinking about that datum, right? Go back. You have 900 columns which represent the images, and a 3 vector that represents your labels. So that's what we're going to do. It's not a lot to go off of. It's fine. It's fine. It'll make sense. You will need to create a new notebook in Colab or wherever it is that you have worked yesterday. And you're going to do problem 1. I put links here. If you're interested in reading more about the various problems, there's this hackathon links page, which actually we kept and have maintained the problem set and all the data for all the problems. We're just going to do problem 1. Just do problem 1, please. Keep it easy. But you can give yourself a challenge in your own time. If you're like, oh, I think I got problem 1, I'll do problem 2. I put this meme in here mainly because the first hackathon I was a part of, it was a tracking detector, and we just had a little fake particle gun, nice head, between -10 and 10 degrees. That's where the tracks will be, and that's what we want is the angle. And I lied to them. We put tracks in there that were at 15 degrees. We put a hole in the tracks, but then put it in our test set. Oh, and it was wonderful in a very maniacal kind of way to sit there and watch teams that thought they knew what they were doing produce a model that gave garbage results because they didn't look at their data. Okay, I was going to lie to you guys and I decided against it. So I did not lie. If you don't do this, it really, don't spend too much time on it. We don't have a lot of time. But out in the real world, look at your data. because you needed to have filtered those out before really producing a model and dealing with all of your data. And then remember Miss Frizzle. Get messy, make mistakes. When you get a solution, test your model. There's model.predict. I can help illustrate how to do that. I assume that most people are going to end up spending a lot of their time just getting a trained model. It's okay. Consider changing the approach. Did you use this dense layer or set of dense layers? Or did you use a convolutional model? Try both. Which one's better? Why? And then the other thing that hopefully you'll start doing as you get a solution is start wondering, is this the best solution? And you'll be butting up against hyperparameter optimization, which is tomorrow's lesson. So feel free to go down the rabbit hole a little bit, but don't go all out. When you get done with a solution, doesn't have to be a working solution. It could be a terrible model. It's still fine. Please save your notebook. Because we can use it tomorrow. We can use the model tomorrow, and then tomorrow you will hyperparameter optimize your model. As a reminder, what you will really need to make sure that you can do this at all, need a way to load the data. It is a CSV with 903 columns. Last 3 are the target values. I missed a parenthesis. And Python and Pandas have some really nice functions for reading CSV files because it's a CSV file. All right. You can use what you want. This is an example of how to read it from the web page using Pandas. Pandas, read CSV. Training CSV. Done. You now have a Pandas data frame that has your 903 columns. You can split out the last 3. Now I have my image and I have my my targets. And you need a loss function. I think it was sparse categorical yesterday. There's one called MSE. So you can use Atom again as an optimizer. Let's not get too in the weeds. And you're going to compile, just say loss equal MSE, mean squared error. Go forth, make mistakes, get messy. I'll be around.
Okay, so the last three columns are the answers.
Are the answers, yeah.
And what we're looking for unknowns are the centroid and the centroid position 1, 2, and the energy.
The energy, the amplitude of the, yeah. So that's your answers. What we would love to do is end up with a model where we could feed it in the hits from our detector, and it would say, this is the position, this is the amplitude. So in nature, we're doing the experiment unknowns would be position, amplitude, energy deposition. But in order to do supervised learning, we have to give it the answers while we train. Once we successfully train, throw that away, and maybe we'll have confidence that it knows how to take in the input and give us the answers. That's the whole premise.
And then yesterday we were doing Atom because I don't see Atom in any of my command.
Oh, yeah, it's buried in the model .compile from yesterday.
Okay.
I believe it was using Atom with 0.001 as the learning rate, but
How much are you?
yeah, so
It was in which one? Sorry.
yesterday's Python notebook, it was in a line called model.compile, and it says optimizer equals, and I think it said something Keras Atom, whatever. Yeah.
Something different maybe.
I know what you mean.
If you, you can kind of steal that, steal this MSE.
Yes.
I highly recommend just do MSE. And then you can steal the lines from yesterday that sets up the Atom, and then you should be okay. But really what I would focus on is read the data in.
Yeah.
And can you successfully give me here is my list of inputs and my list of answers. And that's your first kind of challenge. Put it on the map just for you. So you can go right there.
From my understanding.
Sure.
Yeah.
Yeah, just a second.
To start from. So here. This is problem one.
Yep.
One and there. So we still use the.
Yeah, I created a new notebook. I didn't create a shelf because I really want you to get the experience. of Woody, yes, yeah, perfect. And there's your code block. So, yeah, so this is where you do like import. And feel free to bring up yesterday's and you can kind of get a sense of some of these parts are actually in there, even though you had no clue what you were doing. You were really doing a lot of this, so yeah, if you have future questions, but poke around a bit.
Mhm.